All right, so this one is a homework problem. Says to evaluate this integral, 8 over 9 plus r squared dr. So a lot of these, we have to do some manipulation. We can kind of move stuff around. Ultimately, we want to get it to a form in terms of u that when we integrate, it's an easy one to do. Okay, and easy is relative. If I wanted to start rearranging this together, I'm not doing any derivative, antiderivative stuff. This is just algebra, moving stuff around. Is this equivalent? Can I factor a 9 from the denominator and then rewrite it as 1/9 r squared? Okay. Is this equivalent? Could I rewrite it as that? I can, because this, really, I could write this as the integral of 8/9 times 1 over 1 plus 1/9 r squared. So that constant multiple of 8/9 I can bring out. So that is equivalent. Can I rewrite the denominator to look like that? Instead of saying 1/9 r squared, can I say in parentheses 1/3 r quantity squared? Yes. Okay. So these 4 lines, these are equivalent. I've just kind of been moving stuff around. Any predictions on what I would assign for my u value? Okay, there's a reason why we did that. So if we said u was 1/3 r. So now, when my u is 1/3 r, I have an expression that looks like this. 1 over 1 plus u squared dr. So, correct. So this is the form that if I had tan inverse of u and I took the derivative of this with respect to u, I end up with 1 over 1 plus u squared. Okay, and vice versa. If I anti-differentiate this 1 over 1 plus u squared, I'm going to end up with tangent inverse of u. So that's why getting it to this form is actually helpful. But again, getting it to this form, making this connection, is not easy, or always easy. All right, so we got it to this form. We've identified our u. Now let's keep going. So du dr is going to be just 1/3. And so I could say du is 1/3 dr. Or I could say 3 du is equal to dr. So the only thing I was able to replace is that dr. And remember, because my variables were different, I have a variable in terms of u in my denominator, and then my differential is in terms of r. I don't have the green light to anti-differentiate. I need to get those to be the same. So now I'd write this as 8/9 1 over 1 plus u squared times 3 times du. The 3 I could bring out, so this is 24 over 9, 1 over 1 plus u squared du. Now my variable on my integrand matches the variable of my differential. I have the green light to actually anti-differentiate. 24 over 9, I could simplify to be 8/3. Back. So this is 8/3 tan inverse of u plus c. And then last step, actually replacing our u with the u we chose, which is 1/3 r plus c, is that final answer. But that first few steps of getting it into a form that we can work with, that's algebra, but we cannot forget about all those inverse trig function derivatives, any of the trig function derivatives, whether inverse or not. We did some practice yesterday with Pythagorean identity, so we got to be good on all this trig stuff, what we can do with it. We can't forget about that, because if we can use that to replace pieces to get into a form we can work with. All right, so that's one of your homework problems. You'll have a similar one. Numbers will probably be a little bit different. So last example that I'm going to do is substitution with definite integrals. So what's different between a definite versus an indefinite integral? The bounds. So a definite integral has bounds. So if you had this one, an integral from 0 to pi over 3, tangent of x times secant squared of x times dx, we can integrate this using u substitution. If this was a with calculator problem, plug her in your calculator and go. But I could give you one like this that is a no calculator problem, and we could still do it without a calculator. U substitution is helpful whenever you have some sort of multiplication going on. Like if you have addition or subtraction going on, just go ahead and integrate. You don't have to do anything funny with it. But when you have multiplication in your integrand, that's when that U substitution is going to come into play. So again, we are going to look at assigning a U value. And we want to pick a U value that when we differentiate, it already appears in our original problem. So what am I going to choose for U? So I heard a tangent of x. So what is the derivative of tangent with respect to x? Secant squared of x. Again, that's why we have to be strong on these to be able to see. So du is the same as secant squared of x dx. So this whole back portion of my integrand and my differential are being soaked up, and I can just say, well, that's just du. So now my integral, I'm going to write the s, but I'm not going to put any bounds on it yet. When our integrand was in terms of x, that dx means the change in x, the width of our rectangles. But now we're going to be working in du. So this is u du. So now we're trying to figure out the change in our function u, which is tangent of x. We're not trying to figure out the change in x of tangent of x, secant squared of x. We're trying to figure out the change with it in terms of u. So we need to find new bounds in terms of u. Our original bounds were from 0 to pi over 3. Well, my new bound will come, so my lower bound would be tangent of 0. And my upper bound is going to come from tangent of pi over 3. So we have to take the bounds they give us and our u value to come up with new bounds in terms of u. Unit circle time. So tangent of 0, so we're right here on the x-axis. So remember, tangent of 0 is the same as sine of 0 all over cosine of 0, not theta. What is the sine of 0? 0. What is cosine of 0? So tangent of 0 is what? 0. So my new lower bound in terms of u is 0, but we had to confirm that it would be that. Okay, it's not a guarantee it's always going to stay the same. Tangent at pi over 3. So pi over 3 is up here again. So tangent of pi over 3 is going to be sine of pi over 3 all over cosine of pi over 3. What is sine here at pi over 3? It's what? Root 3 over 2. So this is root 3 over 2. Sorry, I'm running out of space here. I should give myself more space. What is cosine pi over 3? 1/2. So we have root 3 over 2 times 2 over 1, which is just root 3. So my new upper bound is root 3. So when we change our integral in terms of u, we have to change our bounds. Okay, so working with this, so my integral from 0, oh, we don't have to do that. What is the antiderivative of u? Okay, so we add 1 to the exponent, so it's u squared, 1/2 integrated from 0 to root 3. We do not have to put in tangent back into this. Don't replace this u with tangent. We've already accounted for our function tangent to create these new bounds. That's what we were doing down here. So simply leave it as u. And so this becomes 1/2 times root 3 squared minus 1/2 times 0 squared. So final answer, 3/2. Okay, so the big thing I want to get across is when you write a new integral, or an integrand in terms of u, change your bounds. But that work changing the bounds is going to help you out down the road, because then you don't have to change that back to say 1/2 tangent of x squared, because your function is no longer in terms of x, it's in terms of u. And you know u at 0 is 0, you know u at pi over 3 is root 3. So you put those numbers in and you get your final answer. Got it? That's it. 12 examples. Okay? So, nope, tomorrow will not be a work day, but this is due by Wednesday, tonight by midnight. If you want an extension and you feel like you've been putting in a good effort and not putting this off to the last minute, I will give you an extension. You just have to ask me, okay? But if you've been putting a good effort in, continue working for the remainder of this hour. Check in with me at the end of the hour. If you do not think you could finish it tonight, that's fine. I don't want you to spend 5-6 hours tonight stressing out to get this done. I want you to get it done. But I think we can still get it done tonight if you've been working through it.